So some molecules have more than one valid Lewis structure. And we just looked at one that did have two structures that satisfy the octet rule and all the other rules we've been given. Let's look at this one. O3 is ozone. So if we draw this, the Lewis structure for ozone, 3 atoms, they've got to be in line. There are structures that have rings of atoms, but we don't draw those in Chem 1A. Those come in OChem. So don't try to make a triangle out of this. It's not going to do it. So 3 oxygens, that's really the only way we're going to put them together. And then how many valence electrons do we have? 18. 3 times 6, they each have 6, so 3 times 6 is 18. Okay, so I've got 2, 4 with the bonds. 6, 8, 10, 12, 14, 16, 18. Almost. I almost got it. These 2 oxygens are good with an octet, but this one's short. So we have to share more. So I'm going to take a lone pair from this oxygen that has enough and share with the oxygen that doesn't have enough. Okay, so now this oxygen 2, 4, 6, 8, this one 2, 4, 6, 8, this one 2, 4, 6, 8. All good. But imagine that these oxygen atoms are triplets, right? Identical triplets, very rare. And so you look at them, oxygen, oxygen, oxygen. But are they the same person? No, they are individuals. So this oxygen atom is not the same as this oxygen atom. I mean, it could be genetically identical, but it is its own atom, right? And so this one over here is saying, well, why does he get the double bond and I don't? I don't know, why? But it's got the 2 double bonds. So, I'm sorry, it has the double bond, the 2 bonds. So each of these is 2 electrons. So 2, 4, 6, 8. Right. So a single bond is we're sharing 2 electrons between us. A double bond, we're sharing 4 electrons. A triple bond, we're sharing 6. Good question. Well, could we draw it the other way? Sure we could. Let's do that. Sorry, I blanked out there for a minute. Forgot what I was doing. Trying to make them look symmetrical. So which one is better? There's no better, right? They're the same. Well, the truth is the actual structure is neither. So in nature, this molecule exists as an average of the 2 Lewis structures. We can measure bond lengths, and what we observe for ozone is that the bond length between these 2 oxygens and these 2 oxygens is the same. So it can't be a double bond on one side and a single bond on the other. They've got to be the same. So Lewis theory does not handle this well. And so we kind of have a patch for it, but it's not that great. So what we do here when we have 2 equivalent structures is, well, I guess I don't really need to put brackets, is we put a double-headed arrow between them. These are called resonance structures. And resonance structure, in the way it's drawn with the arrow, always brought to my mind that it was like flashing between. You know, it was going back and forth. And so if we measured it, we'd see the average would be the same, but actually it was going back and forth. And that's not true. Yeah, the double-headed arrow indicates resonance, and you put that between, and you can have more than two structures. You could have 3 or 4. So the actual structure is called a resonance hybrid. And so here we have a dog illustration. So if you had a German Shepherd and a white lab, and they had puppies, their puppies might look like this, right? Got some coloring from the German Shepherd, but a lot of characteristics of the lab. Does this puppy look like a German Shepherd some days and a lab on other days? No, the puppy always looks the same, right? But it's a combination of the two parents. It's a hybrid. It's both and neither, right? And so that's what a resonance structure is. Here we have the one with the double bond on the left, and here's with the double bond on the right. And the actual structure is a hybrid of those, a combination. It's between. It's a little bit small there, so I'll draw it a little bigger.
So we're going to figure out how to make this hybrid?
Well, we're going to learn about better theory. Well, actually, we can't even do that. It's just very limited. So just looking at the bonds, you can imagine that there's a single bond, and that other bond that was double is actually split between them, and so you have a half bond here and a half bond there. And Lewis theory just doesn't deal with it, and so we draw the two and say, well, it's a combination. Okay? In the Lewis model, electrons are localized. We have to say the electrons are hanging out with this atom or with that atom. They're between these two atoms. We can't spread them out over the entire molecule. That's called delocalization. But in nature, electrons are often delocalized, and it stables the molecule. That lowering of energy is called a resonance stabilization. Yes? So how do you know if it has resonance structures? That's basically what you're asking. For the most part, if you have a choice when you're drawing it this is only going to happen if you have double and triple bonds. If it's all single bonds, there's no resonance. If you're putting in a double or a triple bond and you have to choose between the same two elements, but different ones, so you have to choose which of these triplets to give it to, then there's going to be resonance.
The reason the H2 wasn't a resonance structure was because we weren't sharing it with.
That's an excellent question. So let's go back. I can't bring back the picture of it, but I can draw it again. So we had these two structures, and the question is, well, is this resonance? And no, these are not resonance structures. For them to be resonance structures, the skeletal structure has to be the same. So here I have 2 hydrogens attached to a carbon, and here I have 1 hydrogen attached to a carbon. These are put together differently, right? It's not just where are the electrons. So these are not resonance. You can have resonance where you have this a double bond between carbon and oxygen, and maybe you could also choose to put it between carbon and sulfur or some other atom. You also can have resonance there. It's generally not very significant, and we'll talk more about that after we learn about formal charges. So Right? A Lewis structure for the NO2 minus ion include resonance structures. So here's another example of resonance structures and a more complicated polyatomic ion. So again, we're going to start with a skeletal structure. We've got a nitrogen and 2 oxygens. How do we put these together? Yeah, probably nitrogen in the middle and an oxygen on each side. Now, there's a couple of reasons I would start that way. One is symmetrical. And 2, it puts the more electronegative elements on the outside and the less electronegative on the inside. And that's how things usually work out. So we're going to go with that. Then we have to figure out number of valence electrons. So nitrogen has 5, and we have 2 oxygens, and they each have 6. And the -1 charge means I have to add an electron, because this has an extra electron. So that looks like 18. Yeah? So then I start throwing electrons around. I've got 2, 4 for the bonds, right? 2 here, 4, 6, 8, 10, 12, 14, 16, 18. Exactly how you do that doesn't matter. I just like to kind of spread it out instead of starting at one end and working over. So we need a double bond, right? Because the oxygen on this end only has 6 electrons. So I'm going to take a lone pair from this nitrogen. Nitrogen's in a good place. So nitrogen can afford to share with this oxygen. So I'm going to take a lone pair from nitrogen and share with the oxygen. Okay? Now the oxygen counts 2, 4, 6, 8, because each bond is 2 electrons. And the nitrogen counts 2, 4, 6, 8. And this other oxygen is still fine, 2, 4, 6, 8. Yay! There we've got it, and it's a polyatomic ion, and so we do need to indicate the charge. So here's nitrogen. Maybe nitrogen is the nanny babysitting twin oxygens. And can you see there might be a fight over who gets the double bond? Because why does this oxygen get the double bond and not this one? Well, honestly, it's random because of how I happen to start putting the dots on there, right? There's no reason. So we can draw it the other way. So here I've got a double bond, nitrogen and oxygen. I wrote it there, but I could put it over here. Same 2 elements. That's what resonance generally is. So I'm gonna draw the same skeleton, just because it makes things easier. And I'm going to put the double bond on the other side.
So the reason why we have to show this resonance is because the oxygens are the same. And
Yeah.
It can go either way.
Yeah, the reason we have to show both of them is because the true structure is a combination, a hybrid. And so actually neither of these is correct. But Lewis theory is limited. And so it can't deal with this. This is the best it can do with the double-headed arrow. And I see that and I say, oh, well, that means that these bonds are actually equivalent. It's kind of like a 1.5 bond and a 1.5 bond. The electrons are delocalized. So this molecule is actually going to be symmetrical with respect to its bonds. Could I draw a structure where oxygen is in the middle and nitrogen is on the end? I could. But that's not going to be a resonance structure of these. If you have to take the atoms apart and put them together differently, it's not resonance. It's just a different molecule. Any questions? So here's a conceptual question. Which structure is not a resonance structure of this one up here? For a resonance structure, you should be able to just move double or triple bonds around, and otherwise it's going to be the same. So this is a little bit challenging. So let's look at the choices and see, well, what's different about them? So here I have 2 double bonds instead of a single bond and a triple bond. Well, could I get that by just taking 1 bond here and sticking it over there? I could. So those are resonance structures. I can just move one of the multiple bonds and I have the same thing. Here I have a triple bond and a single bond. How is it different than this one? The carbon and the nitrogen are in different places. Can I get from this one to that one just by moving a double bond or a triple bond? No. I have to take the thing apart and put it back together differently, right? Here, carbon's holding hands with sulfur and nitrogen. Here, nitrogen's in the middle holding with sulfur and carbon. That's not the same, okay? So that one's not a resonance structure because the atoms aren't connected the same. How about this one down here? The atoms are connected the same way, but the triple bond's over here instead of over here. I could take this double bond and just move it over there and, adjust the lone pairs. And I could get that. This is just a choice of who do I give the triple bond to. This is also a resonance structure. Any questions? Yeah.
Are resonance structures always polyatomic ions?
They are not always polyatomic ions. That's a good question. Any other questions? Okay, formal charge. This will help us to decide what's the best structure. So kind of like oxidation states were made up charges, formal charges are also made up charges. Because here we're talking about covalent compounds, there are no ions. But the sharing of the electrons is not always equal, and so this helps us to figure out which structure is better. So there's two main ways of identifying the formal charge. And the nice thing about this is it's a simple set of rules. We don't have to consider electronegativity or any of the fancy things. This is a simple tool that predicts that with less thinking. So the idea here is we're looking at, well, let's start with the Book's method. You assign a formal charge to each atom in a molecule. The formal charge for that is the number of valence electrons it has as an individual atom, minus the number of non-bonding electrons and half the number of bonding electrons. So if that works for you, great. Personally, I find that a bit confusing. So I will show you my method. Well, maybe just not yet.
So we're not going to use that method?
Well, you can, but I'm not going to use it in lecture. My approach is that we draw the Lewis structure, and then I think of this as like a corporation, and each atom was a person that joined this corporation, and they all brought assets to the corporation, right? Those are their valence electrons. And so then when we break up the corporation, we're just going to cut all the bonds in half and see what these people leave with. Some people will leave with more electrons than they came with, some with fewer, or everybody might go home with the same number. That's formal charge. So do you leave with the same amount you came with? And so it's easier when we actually have a molecule to deal with. But some rules here, and they're kind of similar to those for oxidation states. The sum of all formal charges in a neutral molecule has to be 0. The sum of all formal charges in an ion has to equal the charge on the ion. Small or 0 formal charges on individual atoms are better. And sometimes we can't avoid having formal charges. We can't make one that's all 0. A polyatomic ion has to have, somebody's got a formal charge. Otherwise, there'd be no charge in the ion. So when you have to have formal charges, you want the negative ones on the more electronegative elements. So those are the guidelines. Okay, so here we're going to look at two structures for hydrogen cyanide. And it's in here, but it's too tiny. So the first one, we put carbon in the middle, and we could put a triple bond here, and that would give us, it's using the correct number of electrons, and everybody has an octet. Or we could put the carbon over here, and the nitrogen in the middle. This is kind of like what happened with that earlier example with the H2CO. Like, well, those two perfectly good-looking Lewis structures, but one of them is better than the other. And formal charges can help us. So the idea here, and see how the book made this really complicated table down there. So here we have a corporation of 3 atoms, and they each brought stuff to contribute, and now we're breaking up the corporation, and we're just going to cut all the bonds in half. And remember, at the end of each bond is an electron. So how many valence, oh, I meant to start on the other side. Oh, well, that's okay. How many electrons did hydrogen bring? How many valence electrons does hydrogen have? It brought 1. So it came in with 1, and how many is it leaving with? 1. 0, 1. So 1 minus 1 is 0. So I'm cutting this in half, and the hydrogen's taking this electron, and the nitrogen's taking this electron. Triple bond cut in half. These 3 electrons go with nitrogen. These 3 go with carbon. This is a very, very sad thought, but if, it's not going to happen. If Dr. K and I split up, right? I could take 3 children. He could take 3 children. It's kind of that idea, you know. Except that 2 of them are grown and 1 of them's half grown, so I don't know. Anyway, here's nitrogen. How many electrons did nitrogen bring? How many valence electrons does it have normally? 5. And how many is it leaving with here? 4. 1, 2, 3, 4. It's leaving with 4. 5 minus 4 is 1. And over here with the carbon, how many electrons did carbon bring? 4. And how many is it leaving with? 5. So that's -1. Now, if I add up those formal charges, do they add up to 0? Yeah. 0 and +1 and -1 adds up to 0, which is the charge on this. It's a neutral molecule. So I probably did the formal charges correctly. So we'll leave that one alone, and let's go do the other one. So again, I'm imagining we're just going to cut all the bonds and share equally here. And we're going to look at, well, what did you bring and what do you leave with? Because the best case is where everybody comes out even, right? Nobody lost, nobody gained. It's just all nice and fair. So again, with hydrogen brought in 1, hydrogen's leaving with 1. Hydrogen always ends up with a formal charge of 0 because it brings 1 electron and it can only make 1 bond, and so that's what happens, and it leaves with that. So the carbon in the middle brought 4 electrons, and how many is it leaving with? 4, right? 1, 2, 3, 4. So that's 0. And the nitrogen on the end here brought 5, and it's leaving with 5. And so that's 0. Oh, that seems more fair, right? So this is a better Lewis structure because this has formal charges of 0. This tells us that the electrons are distributed more like they would be in real life. Because, I mean, we're just putting dots around letters, right? That we can't make stuff happen. We can't make stuff happen that doesn't exist. Now, could this molecule be formed? Yeah, it could. But if I'm writing the structure here, I'm going to write this one as the better structure. Now, another thing we can look at between these two, because I kind of wrote up the others there. How many unpaired electrons does carbon have as an atom? 4. So I told you it wants to make 4 bonds. So look here, carbon has 4 bonds. 1, 2, 3, 4. If carbon has 4 bonds, it will have a formal charge of 0. And nitrogen. Lewis structure for nitrogen. It has 5 valence electrons. It has 3 unpaired electrons, predicting 3 bonds. And here, I don't know why I drew those because I ended up using this one. Here, nitrogen has 1, 2, 3 bonds. Over here, nitrogen has 4 bonds. Carbon has 3 bonds. That's not what they would prefer. So, being aware of this little trick can help guide you toward the correct Lewis structure to start with, and then you use formal charges to figure it out. And if you like the book's method, you can do all of that. Any questions? This one also fits that earlier guideline that try putting more electronegative elements on the outside. And nitrogen's more electronegative than carbon, so that would also predict that maybe I should start with this one. Okay. Assign formal charges to each atom in the 3 resonance forms of N2O. N is central. It says that because we wouldn't expect you to do that. I would expect you to put oxygen in the middle and nitrogen on each side, but we're saying, this one's weird, so I'm telling you, nitrogen's in the middle. Which resonance structure is likely to contribute most to the correct structure? The previous 2 structures we were looking at for hydrogen cyanide, those are not resonance structures because they were connected differently, right? So here, these atoms are all connected the same way. We've got nitrogen, nitrogen, oxygen, nitrogen, nitrogen, oxygen, okay? And what's different is where are the multiple bonds? So here we have a double bond on one side and a double bond on the other. Here's a triple bond with the nitrogen, a single with the oxygen. Single bond with the nitrogen, triple with the oxygen. Yes, that sounded like a child. Okay, so formal charges. Let's split things up here and see what we've got. So just cutting up these molecules. We're going to break up and go home. Yeah, got the pink slip. Company's going under. So here's nitrogen. Nitrogen always brings 5 electrons in. 5 valence electron. How many is it leaving with here? 6. 1, 2, 3, 4, 5, 6. So that's a -1. This nitrogen in the middle also brought 5, but he's leaving with 4. It doesn't seem fair. And then the oxygen brings 6 and is leaving with 6. Well, oxygen thinks that's okay. So this would have a -1 formal charge, and this would be a +1, and this one would be a 0. Usually if it's 0, we don't write that it is anything. Okay, so let's look over here. Nitrogen brings in 5 and leaves with 5. So that's 0, right? Nitrogen brings 5, leaves with 1, 2, 3, 4. So 5 minus 4 is positive 1. Oxygen brought 6, and it's leaving with 7, so minus 1. And then over here, nitrogen brings 5, now it's leaving with 7, minus 2 on that one. And this nitrogen brought 5, leaving with 4, right, plus 1. Oxygen bringing 6, leaving with 5, plus 1. Okay, so it came with 6, left with 5. Came with 5, left with 4. No, I did that. Yeah, no, that's right. Sorry. And the one over here came with 5, left with 7. So we assigned the formal charges. And now, which is likely to contribute the most? Well, we're looking for lowest formal charges, and if there are formal charges, to have the negative formal charge on the more electronegative element. So here we have negative 2, 1, and 1. Here we've got plus 1, minus 1. Here we've got plus 1, minus 1. So how do you decide which one has lower formal charges? Yeah, you could add the absolute value, right? And that would give you a number that you could compare. So absolute value of this would be 2 and 1 and 1. This would be 4, and this would be 2 and 2. So these A and B both have lower formal charges overall. And then how do we pick between A and B? Well, who's more electronegative, nitrogen or oxygen? Oxygen. So in B, oxygen has the negative charge. In A, this nitrogen has the negative charge. So this one is the best one. Now, that doesn't mean that that is the only structure and there's no resonance. There will be resonance here because we're just moving double bonds, triple bonds around. We're not reconnecting things in a different way. But these are not identical. This is oxygen and this is nitrogen. And so when they're arguing about why does he get this and I don't get this, it's like, well, you're 2 years older, so blah, 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 right? When they're twins, they're even genetically identical. How do you choose between them, right? So B is the best one because O has the negative charge. So we're looking for who's most electronegative. So then we look at the periodic table and we see that oxygen is closer to fluorine. Oxygen is more attractive to the electrons. And in this middle structure, that electron that's not distributed equally, because we can't do this and have 0 formal charges, right? There aren't any other possibilities. Here we have the negative, that extra electron on the oxygen, where it's going to be happier because that's the more electronegative, it's more attractive to the electrons. This is more likely to happen than over here, where the extra electron's going way over there for we don't know what reason. Any questions? Other than who has the kid in the lab next door? At least it's a happy child. Mostly. Okay, let's practice. Draw the Lewis structure, including resonance structures, for diazomethane. CH2N2. And I'm telling you that carbon is central. For each resonance structure, assign formal charges to all the atoms that have formal charge. Well, we're told that carbon's in the middle. So there's carbon. Hydrogens must be on the carbon. Well, not necessarily. Let's try attaching everything to the carbon and see how that works. I said carbon's in the center, so let's try that. Well, we have to figure out how many valence electrons. We have 2 hydrogens, they each have 1 valence electron. We have 1 carbon, 4 valence electrons, and we have 2 nitrogens, they each have 5. So that is what, 16? So I need to represent 16 valence electrons in my structure. So I have 2, 4, 6, 8, 10, 12, 14, 16. Okay, used up all my electrons. That means I need to do more sharing. I need to make a multiple bond. Well, carbon's the guy who has enough, but there's no lone pairs on the carbon. So I can't take a lone pair from carbon and share with nitrogen. If I take a lone pair from nitrogen and share with carbon, that's not going to work because carbon can't have more than 8 electrons. It can't break the octet rule. So I don't see any way out of this one. This looks like it's just not going to work. So we're going to have to move something around. Well, what if we took this hydrogen and stuck it on one of the nitrogens instead? Let's try that. We'll swap, well actually, put it over here, put the hydrogen over here. So I just moved the hydrogen. Well, now this nitrogen has 8, and it has lone pairs, so it could share with the carbon, right? So let's try that. So nitrogen's happy, hydrogen's always happy. The carbon's happy, but the other nitrogen, not happy. Yeah, so we're going to have to do the same thing because this carbon can't double bond with the nitrogen because of the hydrogen. So we're going to put the hydrogen on the other nitrogen. Just move it around. Pencil is really good for Lewis structures. So now this nitrogen has 8, the carbon is missing, and so we can take a lone pair from the nitrogen and share with the carbon. And we've got octets for everybody. And it looks like it's all twisted up on itself, right? That sometimes happens when you're drawing them. So I'm going to draw it again over here, but just make it look a little nicer. So I just straightened him out. Now, the question is suggesting that there are resonance structures. They don't know what they're talking about. On to the next slide. No, actually, they're right. Well, we've got double bonds here. Could we move one of these double bonds over here and have a triple bond and a single bond? We'd have to move this lone pair, but let's see if we can do that and if that works out. Yeah. So single bond here, triple bond over here, and then we'd have to have 2 lone pairs on the nitrogen over there. 2, 4, 6, 8, 10, 12, 14, 16. Correct number of electrons. Everybody's still in an octet, right? And then you can imagine this nitrogen say, well, why does he get the triple bond? Because we happen to put it there. Well, I want it. Well, okay, fine. Here's your triple bond. So these are resonance structures. You see how they're resonance structures? The atoms are in the exact same order, connected in the same way. What's different is where the multiple bonds are. Here we've got on each side of the carbon 2 and 2. Here we've got 1 and 3, 3 and 1. Just where are we putting those shared electrons? So it says, assign formal charges to all atoms that have formal charge. So this is where knowing how many bonds different elements like to make can make this easier. So hydrogen has 1 valence electron. Carbon has 4 valence electrons. Nitrogen has 5 valence electrons. Hydrogen likes to make 1 bond. Carbon likes to make 4. Nitrogen likes to make 3. If nitrogen has 3 bonds and an octet, it will have a 0 formal charge. If carbon has 4 bonds and that gives it the octet, it will have a 0 formal charge. So when I'm looking at this structure up here, this nitrogen has 1, 2, 3 bonds, and this nitrogen has 3 bonds, and the carbon has 4 bonds. So this, all 0 formal charges. We can also kind of prove it to ourselves by putting this on the chopping block. Well, hydrogen we never have to worry about. So nitrogen brought 5 electrons, and it's leaving with 1, 2, 3, 4, 5. Carbon brought 4, it's leaving with 4. This nitrogen brought 5, leaving with 5. 0 formal charges. Down here, we see this nitrogen has 4 bonds. The carbon here has 4 bonds, and this nitrogen has 2 bonds. So I can tell that this carbon's going to have a 0 formal charge, and the nitrogens are going to have some charge, non-zero. So here, carbon brings 4, leaves with 4. 1, 2, 3, 4. 0 formal charge. Over here, nitrogen brings 5, always brings 5. How many is it leaving with? 6. 1, 2, 3, 4, 5, 6. So this has a -1 formal charge. And this guy over here brought 5, leaving with 4. So that's a +1 formal charge. Okay? Do we have to go through all of that for this one? No. These are just in the same but opposite situations, right? So this nitrogen arranged like that had a -1 formal charge, so now this one has the -1 formal charge, and this one has the +1 formal charge. That's what the question asks. If it said, which structure contributes most to the resonance structure, the answer would be this one at the top, because this is where all the formal charges are 0. Any questions?